welcome back to the second module of the fourth week in parameterized algorithms. So in this week, we have been exploring how we can leverage the power of randomness to come up with interesting FPT algorithms for a wide variety of problems. And in this particular video, we will be considering the long path problem, or the longest path problem if you prefer the optimization version. And in a previous undergraduate algorithms course, you may have seen the short path problem, or the problem of finding some shortest path between a pair of vertices. So this might remind you of that. In some sense, this is the exact opposite optimization objective. So you really end up looking for paths that are as long and drawn out as they can be, instead of looking for ones that are as short and quick as they can possibly be. Now, unlike the shortest path counterpart, the long path problem does turn out to be NP complete, which is why it's meaningful to look for FPT algorithms for them. And we will be working with the standard parameter here, which would be the size of the path, which we think of as the solution, and the parameter therefore will just be the solution size. Now, the technique that we will introduce to solve this problem is called color coding, and it turns out that it's this really elegant and simple technique which is also extremely powerful, and it has evolved to become a really popular technique both in theory and practice since it was first introduced in about 1995. So with all that said, let's get started with the definition of the problem, and then we'll talk about the overall random experiment, and as usual we will try to understand what is our concept of a good event, and then we'll try to justify why the good event is actually good for us, and then we'll come back and analyze the probability that the good event actually occurs, and with that we will be able to wrap up our analysis. So let's begin by formally defining the long path problem. So here we are given as input a graph G and a positive integer k, where G we will assume as always is a simple and undirected graph on n vertices, although the problem definition carries over very naturally to directed graphs as well. Our focus in this discussion will be on our usual default setting, which is that G is undirected. Now, the question we are interested in is whether G has a simple path of length at least k, and there are a couple of keywords there that are worth emphasizing and clarifying. The first one is the notion of length. So for us, the length of a path is just going to be the number of vertices on the path. So we're really looking for a path on k vertices, and k vertices or more. And the other adjective here is simple. So by a simple path, we mean a path where vertices do not repeat. Now, depending on which book you are reading, some people would just not use the adjective simple and would just use the word path to refer to a sequence of distinct vertices where every pair of consecutive vertices has an edge between them, and will use the term walk to refer to the possibility that vertices can repeat or they don't all have to be distinct, whereas in other sources a path would by default allow for repeated vertices, and you use the adjective simple to emphasize that repetitions are not allowed. So in any case, here we just want to be quite clear that we do not allow for repetitions. If you do allow for repetitions, then the things that you're looking for, let's call them walks, are somehow much more tractable computationally. And we will be revisiting this notion sometime later in this course, so I'll not get into it very much here. Just keep in mind that what you're looking for is a sequence of k distinct vertices such that every pair of consecutive vertices has an edge between them. Notice that it doesn't have to be an induced path, so you could have other edges going around here, but at least these edges must be present. Now notice that k-path generalizes the Hamiltonian path problem, which essentially asks if there is a path that visits every vertex of the graph exactly once, and that's essentially k-path with k set to n. So I'm sorry that in this diagram what's highlighted is a Hamiltonian cycle and not a Hamiltonian path, but you get the picture. Hamiltonian path is a classically well-known NP-complete problem, and because k-path generalizes Hamiltonian path, it's also NP-complete. So from the parameterized perspective, a natural parameter here is the standard parameter, which is k, the size of the solution that we are looking for. And I would encourage you to pause here for a moment and think about the question of whether you can come up with some sort of an algorithm for long path, keeping k in mind as the parameter. What would be the complexity of, let's say, a very naive first cut brute force approach? Give that a thought and come back when you're ready. Okay, so if you tried the brute force approach, you would probably have to go over all possible subsets of size k as candidate solutions. And for each subset that you consider, you would probably have to try all possible ways that you can sequence that subset and check if that forms a valid path or not. Now, this is going to be at least n to the k time just for enumerating all the subsets, and now you already know that this is not looking like a FPT running time at all. So we really want to ask ourselves if we can come up with a FPT algorithm, and what we are going to describe next is a randomized FPT algorithm that has in fact a single exponential running time, and let's explore how this works. So I will begin by describing the random experiment that we are going to perform. So as usual, let me try to describe this with the help of an example. Let's say this is our graph G, and suppose we are looking for a simple path on 4 vertices. The random experiment that we are going to perform is the following. What we will do is we will go to every vertex in the graph and try to assign a label to it uniformly at random, where the labels can be thought of as being numbers between 1 and k. So in this case, the numbers will be from 1 to 4. Now, this is called color coding because it's useful to visualize this labeling process as some sort of a coloring process. So you can visualize every vertex is getting one of k distinct colors. So you have a palette which has k colors, and what you're doing is coloring each vertex with one of these k colors. Continuing with the example, let's say the palette we are working with has the colors red, yellow, blue, and pink. What we want to do is essentially color each vertex with one of these colors uniformly at random, and notice that these events happen independently for each vertex. There is no correlation between any subset of vertices. It doesn't depend on the structure of the graph. You just go to each vertex and you perform this labeling exercise or the coloring exercise completely independently. So at the end of the experiment, your graph will end up looking quite colorful. Every vertex will have a label or a color between 1 and k. And now the natural question is, what is the good event? What are we hoping will happen as a result of this experiment? Notice that we are still working with these one-sided error algorithms, so we really want to cross our fingers when we are working with yes instances. So we are hoping for something specific to happen when the graph does have a path of length k. And intuitively, what we are hoping for is that this labeling helps our path somehow pop out. And if you imagine the labeling as partitioning the graph into k different paths, the hope is that if there is a solution, if there is a path on k vertices, then it somehow gets spliced across these paths. And in thinking in terms of colors, the hope is that the path gets colorfully colored, which is to say that colors don't repeat on the path. So formally, we say that a path P is colorful with respect to a coloring sigma if no pair of vertices on this path have been assigned the same color. So every color is used exactly once on this path. So if we go back to our example and we look at the random coloring, you will see that this is indeed a good coloring for us because there is a path on 4 vertices and it has been colorfully colored. So hopefully you are able to identify both the path as well as the fact that we did end up with a lucky colorful coloring. Okay, the next question that should come to your mind now is, well, all this is well and good, but how does a colorful coloring help? So suppose I give you a colored graph with the promise that, if there is a path at all, there is a path which is also colorful. Then can you use this information to actually find path relatively quickly? And here by quickly, we just mean using FPT time. This is a good place to pause and think about whether you can come up with an algorithm if you are in the good situation. Just assume for now that the good situation does manifest. We will come back and discuss the probability that the good event actually occurs. So for now, just take it as a given, give it a thought, and come back once you are ready. All right, hopefully you had a chance to think about this. Notice that the answer to this question will justify our concept of a good event, right? So if we are able to identify colorful paths quickly, then it makes sense that we would like our random coloring to color a solution in a colorful way. So let's go back to the good situation and just stare at what that looks like. And instead of tracing out a colorful path, let's just try to look at this situation from a different perspective. Remember, we said that you could think of a K coloring as a partition of the graph into K paths. So let's try to think of this in terms of the partition into these color classes. So what we know at this point is that there is a path that visits each color class exactly once, but what we don't know, for example, is the sequence in which these colors appear on the colorful path. So for instance, it could be that the path begins at red, goes to pink, and then yellow, and then blue, but it could also be that it begins at pink, goes to yellow, then blue, and then red, or it could even be that it starts at blue, then pink, then yellow, and then red. We don't really know this sequence. So what if we did know this sequence? So what if this was given to us? Let's say somebody told us that, look, this colorful path actually starts with a pink vertex, then it visits a red vertex, then it picks up a blue vertex, and it finally ends at a yellow vertex. Is this information useful? Because notice that if you can actually exploit this information, then this information is not very expensive to guess. Notice that there are only k factorial ways in which the colors can be ordered. So we can sort of guess the sequence in which the colors appear on a hypothetical colorful k path. So let's fix a guess, let's fix an explicit guess and try to figure out what would we do with this additional information. So if you didn't have it figured out when you took the pause previously, this is a good time to pause again and see if with this extra information now, can you come up with an algorithm to detect a colorful K path if it exists. Notice that in this picture there are many edges that are completely irrelevant, so see if you can delete some edges, clean up the graph, and use an elementary graph algorithm to check if there is a path of length k or not that is colorful. Come back once you're ready. Okay, so once again, hopefully you had a chance to puzzle this out a little bit. Notice that once you fix the sequence of colors on the solution that you're looking for, a lot of edges do become useless to us in that we know that they will never feature in this solution. In this particular example, we know that the path consists only of edges whose endpoints have the following color combinations: pink and red, red and blue and yellow. So any edge whose endpoints have a different combination of colors, say edges that have both of their endpoints within the same part, or edges whose endpoints are, for example, pink and blue, or yellow and red, or yellow and pink, these are all edges that are not relevant to us at all. So we can simply erase these from the graph. After that, we're just left with the edges that go between the consecutive parts of this partition. From here, what can we do? Well, we want to know if we can go from the leftmost part to the rightmost one with, through a path. So So one way to do this is to, for example, orient all of these edges from left to right and add an artificial global vertex to the first part of the partition. Also orient these edges from the global vertex to the first part, and now you have this nice simple directed graph, and you could start a BFS from this artificially introduced global vertex. So why is it useful to do a BFS starting from this source vertex? Well, notice that if there is a colorful path of the sort that we were looking for, then this colorful path is also a shortest path from the newly added global vertex to the last vertex on that path itself, which in this case happens to be a yellow vertex. The reason this is the shortest path is practically by design, by the way in which we have eliminated all the other edges in the graph. So in particular, all the vertices at distance 1 from the newly added source vertex or the global vertex are exactly the vertices in the first color class. In this case, that's all the pink vertices. The vertices which are at distance 2 are all the red vertices, and those at distance 3 are the blue vertices, and so on and so forth. So just running a BFS will essentially capture exactly what we needed to capture. So if the last color class is reachable from the source vertex, then the path that you obtain from that is a colorful path of length 4 by definition. And if it is not reachable, then, well, you couldn't have had a path of length, a colorful path of length 4 in this setting, because such a path would have been detected by the BFS. So I hope that that makes sense. And by paying this expense of k factorial upfront, what we finally have is a nice polynomial time algorithm for detecting a colorful path in the setting of a lucky event, right? So if we had a good situation from the random experiment, then we have a k factorial times poly n procedure to figure out if a path of length k exists or not. We simply take all the color classes, line them up in all possible k factorial ways. We do these simplifications that involve deleting some edges, orienting some edges, and adding an artificial source, run a BFS, and we are pretty much done. So that is a nice, simple randomized algorithm for detecting the presence of a k path. The only thing that remains to figure out is, well, how often do we get lucky? Do we get lucky with a decent enough probability that our boosting trick will guarantee us an overall FPT algorithm? So let's talk about the analysis of the probability that a good event actually happens. So let's recall the concept of a good event. Recall that we have been saying that a random coloring is good for us if it colors the vertices of a path on k vertices, if it exists, of course, distinctly with all different colors. So in the running example that we've been working with, k has been 4, so we've been working with a palette of 4 colors, blue, red, pink, and yellow. And what we want is that if there is a path on 4 vertices, then it should get each of these colors. The 4 vertices on this path should be colored with each of these colors exactly once. Now, how do we analyze the probability that a random coloring does have this property? By the way, let me just get one small thing out of the way. Notice that if a graph is a yes instance, it may actually have multiple witnesses to the fact that it's a yes instance. In other words, there may be several paths of length at least k. Even in this example, it's not very hard to find other paths on 4 vertices. However, in the spirit of doing a worst case analysis, we'll just focus on the probability that an arbitrary but fixed path in the graph is colored colorfully. This is sufficient because in a yes instance, you're going to have at least one path, so we might as well fixate on any one of them. It doesn't matter which one, but just fix your attention on one path and compute the probability that that gets colorfully colored. If that's a decent probability, then in the real world, when your graph actually has multiple solutions, the probability that any one of them gets colorfully colored will be, if anything, even better. So it's enough to just do this, and notice that in the worst case, if your graph happens to be such that it has only one solution, this calculation will also account for these kind of extreme cases. Okay, so with that out of the way, let's just consider what is the probability that this arbitrary but fixed path on k vertices gets colored in a colorful way. Now, the way we calculate probabilities is fairly standard. We look at the number of events in the sample space that work out in our favor, that are good events for us, and then we look at all possible things that could happen, good and bad put together. So we really need to answer these two questions. The first is, what is the number of ways in which these k vertices can be colorfully colored with k colors? Those would account for the good events, and to account for all situations, we need to understand what are all possible colorings, what is the number of all possible ways in which these vertices could be colored. Now, the ratio between these two would be the probability of the good event. Now, please take a moment here and try to answer both of these questions, which are not very difficult. If you have pen and paper handy, please just try to work through it. Both of these are fairly straightforward counting questions. Do come back once you've had a go at it. Alright, first let's consider the number of ways in which these k vertices can be colorfully colored. Since we have k vertices and k colors, and what we really care about is the fact that every vertex should get a distinct color, what we are really looking at is a permutation of these k colors. So for these k vertices, there are k factorial good scenarios, and for each of these good scenarios, the remaining n minus k vertices can get colored in whatever fashion we don't really care. So for each of the k factorial permutation colorings, on these k vertices, we can extend these colorings to colorings of the complete set of n vertices by coloring the remaining vertices in any way we like. Now, what are the number of ways in which we can color the remaining vertices? There are n minus k vertices that remain, and since we don't care about how they are colored, there are no restrictions. They can be colored in k to the n minus k different ways. Each of these vertices have k choices of labels, and all of them are valid. So the total count is k to the n minus k times k factorial for the good event. Now, for collecting the total number of events, that's really just looking at all possible colorings. So that's going to be just count all possible colorings with no constraint. So that's going to be k to the n, but just to make it easy for us to simplify, I'm going to break that down as k to the n minus k times k to the k. So we see that the k to the n minus k term cancels out, and what we are really left with is k factorial over k to the k. Now, it turns out that k factorial can be lower bounded by k over e to the k. This is a standard inequality, and it's quite helpful in this case because now you see that the k to the k cancels out and we are left with 1 over e to the k. Notice that if you apply the boosting arguments that we have discussed in the previous module, you can get this up to a constant by simply repeating the random experiment e to the k many times. So now let's put everything together and take a look at the overall running time. So what we have is e to the k coming from the boosting part of the argument, the repetition of the random experiment, and we had this k factorial amount of work that we did when we guessed an ordering of the color classes, and then we did a little bit of cleanup, simplifying the graph a bit, adding a source vertex, and then running a BFS. So all of that was a polynomial overhead. So right now we have a running time that looks like e to the k times k factorial, which is a pure function of k, multiplied by a polynomial in n. So this is very much a randomized FPT algorithm for the problem of finding a path of length at least k. So we are pretty much done, but a question that you can always ask yourself at this stage of the discussion is the question of whether we can do better. In particular, can this running time be improved? And notice that as far as this algorithm is concerned, there are two major components to the running time. The first is e to the k, which comes from repeating the random experiment so that we are confident about the success probability. This is the boosting part. The second component is the k factorial poly n, which is the work that we needed to do to find a colorful path under the assumption that the good event actually panned out. Now, it is the second part that we can actually replace with a different approach, which is slightly more sophisticated and gives us a better running time. In particular, we can improve the k factorial to 2 to the k using dynamic programming over subsets of colors instead of trying out all possible sequences. So let's go ahead and discuss what that could look like so that we get this improvement in our running time. So remember that the input at this point is a colorful graph. Well, I shouldn't use the term colorful, it's a colored graph. Every vertex has been assigned one of k different colors. In this example, we are just going with k equals 3, and the three colors are blue, red, and yellow. And the question is, if this graph has a path on k colors that is colorful, which is to say that every color is used exactly once. So what does the DP table look like? Well, its rows are going to be indexed by the vertices of the graph v1 through vn, and the columns are going to be indexed by the subsets of colors. So there are 2 to the k columns. Each column corresponds to a different subset of colors, and you could just organize them in increasing order of size. And when you're looking at subsets that have the same size, it doesn't really matter how you order them. So notice that the size of this DP table is 2 to the k times n. So that looks promising. I mean, at least if we know how to fill out this table efficiently, and if we can give it some meaningful semantics, then perhaps we are on the right path. So what are the semantics of this DP table? What do we want to populate it with, and when do we populate it one way or the other? Well, so let's consider the entry corresponding to the subset S and the vertex U. So this is the row corresponding to the vertex U and the column corresponding to the subset S. We are discussing that entry. So this is going to be a table with Boolean entries. So the entries will be 1 or 0 or true or false. You can pick whatever terminology you like. And the semantics is that the value is 1 if there is a colorful path ending at U that uses colors exactly from S. So here our notion of colorful is just that colors do not repeat. So you have some path that ends at U using colors exactly from S, which is to say that every color in S is used exactly once. That is the sense in which we want the path to be colorful. Notice that this is fairly intuitive in the sense that if you're used to thinking about DP as an approach that builds on partial solutions, this is the natural projection of the notion of a colorful path of length k to sort of smaller paths. So the natural projection is that you're colorful but with respect to a smaller subset of colors. So is this a useful semantics to work with, in the sense that if we do manage to fill out the table with the semantics, will we get to our answer? This is a good place to pause and think about whether the answer to your original question, which is, does G have a colorful path on k vertices? Can you find that answer from this table if the table was correctly populated with these semantics? Okay, so hopefully you had a chance to think about that. Notice that the ultimate thing that you're looking for, which is a colorful path on k vertices, is essentially S being equal to 1 to k. S is the set of all colors. It's the subset corresponding to the universe, the full set of colors. And you know that if a colorful path exists, well, it must end at some vertex. We don't know which vertex, so we will simply try all possible vertices, right? All possible choices of the last vertex on the colorful path that we are looking for. If there is a colorful path, then at least one of these DP table entries must be 1. And if there is no colorful path, well, of course, then all all of these entries must be false. So by just doing an OR over these n entries, so essentially taking a Boolean OR over the last column in the table, you get to your final answer. So clearly these semantics are useful. If we manage to populate the DP table with respect to these semantics, then we would be done. So the only thing left to discuss is the recurrence. Once again, at this point, I would strongly recommend that you pause and think about what the recurrence would look like. How would you populate this? I will in fact not discuss the base cases because they are completely straightforward, and hopefully you'll be able to figure those out for yourself. In case you have any questions, please do ask at the forums and we'll be happy to clarify further. You could also look at the notes on the course website where there are more details. But for now, let's just focus on the recurrence, and I hope that you're able to pause and think about this for a bit and come back when you're ready. Okay, so let's take a look at a generic entry dp s comma u, and just to make this a little bit concrete, let me assume that u itself is colored yellow. It could be any color, it's going to be some color. So of course the first thing we want to ensure is that this color belongs to S, because we're looking for a colorful path which is colorful with respect to S, which ends at U. So the path itself includes U. So if this color does not even belong to S, then all bets are off. We just set this entry to false and move along. But if this color does belong to S, then, well, then we can focus on the rest of the path and notice that the penultimate entry on the path, the path ends at U. What was the previous vertex? Well, the previous vertex must have been some neighbor of U, right? So, well, we don't know which neighbor, so we're going to try all possible neighbors, and we're going to look up the DP table entry corresponding to, well, paths ending at those neighbors. We try out each neighbor as a candidate for where the subpath should have ended, and of course we'll have to remove the color of U from the set S because we have already used this color. We're not allowed to use it again. So you just have to go ahead and look up these DP table entries, and if any one of them is 1, then what does that mean? Well, that means that you do have a colorful path using all colors in S except for the one that was already used on U, and such a path in fact ends at a neighbor of U. So you know that this path can in fact be extended to a path that ends at U and uses all colors in S exactly once. So if the right hand side of this equation evaluates to 1, we know that the left hand side must evaluate to 1. On the other hand, if the left hand side is 1, which is to say that you do have such a path, then, well, just look at what neighbor of U did that path end just before it actually ended at U. That subpath of length size of S minus 1 will be a witness for some entry on the right hand side to be triggered to true. So therefore we see that this equation makes sense, this recurrence holds, and of course you do have this top level sanity check that the color of U must belong to S. So if the color of U does not belong to S, then it's anyway false. Otherwise the value of the DP table entry is completely determined by the entries that have been shown to you on the right hand side of this equation. So I hope that this recurrence makes sense. You can see that computing any entry of this DP table is just a polynomial amount of work. In fact, it's just proportional to the degree of the vertex U. That's the number of table lookups that you need to do after a simple sanity check, and therefore the overall running time is simply the size of the table, which was 2 to the k times n, times a polynomial overhead. So basically that's the improvement that we claimed, and that's the improvement that we now have modulo a description of the base cases. So of course the base cases are very important. Your algorithm will not run without it, but they're also fairly easy to fix up. So I'm going to leave that as an exercise, again with the invitation that you should feel free to reach out or just leave a comment in case anything about the base cases is not clear. So I hope that made sense. This is a really fun technique technique, and as I said, it's applicable well beyond long path, and I think the assignment questions should give you some practice on how this can apply to other patterns as well. So do have fun with that, and I'll see you in the next video with a slightly different version of the color coding technique. Thanks for watching, and bye for now.